So in this video lecture, I'll be talking about optimization and really just an introduction to what optimization is, and then we'll be moving into how to use it for mechanism design in just a moment. So first of all, I'm going to talk about what are some limitations of the existing precision position methods, and then getting into how do we formulate an optimization problem, and then specifically talk about a few algorithms and give some examples of simple optimizations. So first of all, we have been spending a lot of time in class talking about precision position synthesis. And so for example, this motion generation problem where we're trying to put the kayak up on top of the vehicle, this is a classic example of having 3 or maybe 4 precision position synthesis, and it works quite well for this because one, we get exact solutions at those 3 or 4 precision positions, but we do have some challenges. One is that we really can't guide the motion in between these 3 or 4 precision positions, so it would be nice sometimes to help guide that motion, especially if we have more complex motion that we require. We're also limited by the synthesis procedure, at least with motion generation, to 5 positions, with path with prescribed timing also with 5 positions, and so that might not be enough for what we're trying to do. And then also, it results in having a need to do the synthesis and then analyze and then iterate and keep going back and forth, because many times you're going to synthesize solutions that are not good and then have to generate new ones and evaluate those. So there's certainly some limitations of the precision position methods that we've been looking at. So what are some options? One is kind of an early step in optimization, which is to say, let me have a few precision positions, maybe 2, pickup and placement at perhaps a nest, and then I can have kind of accuracy neighborhoods around other positions. And this is kind of a common way of attacking this, where you can add more precision positions and say, let me approximately hit these intermediate ones. But let me talk about some other optimization techniques as well. So first of all, a quick definition of what is optimization. It is just finding what are the design variable values to either minimize or maximize an objective function. And an objective function is basically saying, you know, do I hit the precision positions that I want to, or do I get transmission angles that are acceptable, and I'm trying to maximize transmission angles or something like that. Now, within optimization, there's many kind of sub-categorizations that we can look at. First is how many objectives there are. We could have one objective, which could be that I just want to hit a certain path and be as close to those path points as possible. Or I could say I want to hit that path and I want to maximize my transmission angle. Or I want to do that and perhaps have something dealing with the balancing of my mechanism. Lots of different objectives that we can have, or ways to evaluate how fit or how well does the solution meet the needs. The second is we can look at multiple domains. So in this class, we've been primarily focusing on the kinematic domain, but recognize that we can have problems where we're considering the kinematics, not only the motion or the path or the function, but also we can think about other issues as well, and I'll be doing some examples later on where we're looking at what is the stress in an element based on a force analysis, which we have to do the kinematic analysis to do it. So many times we have different domains that we have to include in these problems. And then once we formulate our problem, we can solve it in a variety of different ways. There are a whole host of different ways, and I'm not going to spend a whole lot of time going into different types of methods, other than to say that there are quite a few that are gradient-based methods where we're looking at local slopes and trying to follow those down. Those are very powerful, but can have problems getting stuck in what we call local minima, and I'll explain what that means in a moment. But then we have a whole host of other ones that help us get out of those local minima, such as genetic algorithms, which I'll do a demonstration of in a little bit. All right, so let's talk about how we formulate a simple optimization problem. So on the right here, I happen to have a plot of just 2 sine waves added together of 2 different frequencies. And let's say that we are wanting to find the minimum of this, from 0 to 50 of this function. So first of all, to help me formulate this, I need to say, what are my input parameters? And these input parameters are the pieces of fixed information. So in other words, a piece of fixed information here is that I have this frequency here divided by 6. That would be a fixed value that is not going to change as I iterate through solutions. Now my decision variables, these are the ones that I'm going to modify to change what the fitness is, or what the objective function is of my solution. And in this case, my decision variable, I simply have 1, which is x, which you see in both sine of x and x over 6. And then I have the objective function. And in this case, this is just f of x which is what I have plotted here on the right. And this is our objective here, and my objective is going to be to minimize this, supposed to have an animation there, going to be to minimize this objective function. So I will minimize. The other common option is to maximize a function. And then I can have constraints as well. These constraints might be on what are the bounds of the decision variables. So this might be from 0 to 50. I could also have additional constraints that could be imposed on the problem based on, perhaps a minimum transmission angle or other things like that. So I'm going to jump to MATLAB in just a moment, but let me just give you a couple of very common MATLAB commands that are used for optimization. And these are used at the command line. So one of them is fmin-unc, which is for an unconstrained multivariable optimization, or a minimization in this case. If you happen to have a maximization, you can just say 1 minus that. Or fmin-con, which is then able to add constraints to the problem, so you're not only minimizing something, but you're also including constraints. There's quite a few others, including some built-in genetic algorithms, but these are the two that I just wanted to quickly highlight. So with that, let me jump over to MATLAB. So now that I've opened up MATLAB, first of all, I'm going to show you a function that I have created. Very simple function that I have named double sine, and just a generic name. But the way I create a function is just open up the editor, call it function, y is equal to double sine of x, and then within the actual function call, I'm going to say y, the output variable, is equal to sine of x, the input variable, plus x over 6. Very simple function, but now allows me to call double sine of some variable, and it will then spit this back out. So just to demonstrate this, let me go back to the command window, and here I can, first of all, let me define a variable. Theta is equal to, let's vary it from 0 to 50. So 0, 50, and how about 1,000 points in between there? I'll suppress the output, and then let me create a figure where I will go ahead and plot theta versus the double sine function. So plot theta, and then the double sine underscore sine of theta. And so now when I plot this, I should get the exact same thing that I had just shown you on the other screen. So here is the output y as a function of x. Now what my objective here is to try to find the minimum value. So looking at this, I can say the minimum value is right around 30, and it should be right about -2. Let's see if we can find that with some commands in MATLAB. So the first command I'm going to use is just the unconstrained minimization. So let me call, first of all, I'll say the output is going to be the value x, and I want to know what the function evaluations are, and I'll say this is then equal to fmin-unc, so this is an unconstrained minimization, and I'll call this double sine function that I just created, double sine, and then I forgot I need to put this in single quotes, and then I will give it an initial guess for a starting point. So let me just go ahead and start with maybe 12 as an initial guess, and then I can go ahead and run this. And first of all, you see that it kind of kicked me out an error, and this was just telling me that I hadn't applied there's no gradient that I was giving it, so it has to pick an algorithm to use. And then it tells me that my minimum value is going to be at x is equal to 11, so I can see that it is right over here, and it's finding a minimum, but it's a local minimum, and the value of it is just under 0. So it is doing its job in that it is moving down starting at 12 here and moving back to 11, but it has not found the global minimum of the problem. So this is a very common issue that we have where we'll find local minima, but not necessarily the global minima. So now I'm going to be using a different optimization function. Let me apply here, instead of fmin-unc for the unconstrained optimization, let me apply a different one here, which is uses a golden search algorithm, fmin-bnd. And here I have to, instead of giving an initial guess, I have to tell it what bounds do I want to apply. So 0 to 50 will be the bounds. And now it does find the global minimum of 29.8 at almost -2. So 29.8, it is finding the global minima of the problem from 0 to 50. So what algorithm I use does make a big difference. And there's a whole host of a variety of algorithms. And it really depends on what the problem looks like as far as the shape of it. Here I've got a problem that has lots of local minima that we can get stuck in, and in some cases we have to go to a little bit more powerful algorithm, such as a genetic algorithm. So a genetic algorithm works something like this. It really tries to emulate what happens with evolution, and so we can think about evolution of animals or plants or whatever it is. But the way we do this is we first of all start the genetic algorithm, tell it, we're going to run it. Here's the optimization objectives, the design parameters, or the design variables, the parameters, and so on. And then I'm going to create a population of individuals. And what I mean by this is perhaps for a mechanism problem, I could create a variety of link lengths that would define a 4-bar mechanism. And I would do that for many different 4-bars. We call these individuals. So this could be members of a population. And then I'm going to evaluate the fitness of each one of these individuals, which means I basically run the objective function and say, if I'm trying to design a mechanism that hits 3 or 4 points, I'm going to say how close does it do that and come up with a value for that fitness. And then once I have the fitness of the individual evaluated, then I'm going to say, let me pick the best individuals to move on to the next generation. So these best individuals will then be bred, is what we call it, where basically we take the chromosome information, meaning the link lengths and everything else, we have it in binary values, and we overlay these such that we basically create offspring that are gaining information from their parents. I then want to create a little bit of new information in this next generation, and so we perform what's called a crossover, where we take the parental information and then mutate it a little bit, so we'll flip some 1s and 0s in our system. And then I will randomly generate possibly a couple of additional individuals, but then I will evaluate all of these again with their fitness and go on and go in a circle in this until I've said I've done enough generations of my problem. So very often we might have a population of, say, 100 different individuals and maybe 50 generations that I would be going through. So I would be making 100 times 50 individual evaluations and hopefully improving as I go on to the point where we can then say, all right, once I've hit it 50 individuals, then I'm going to end the genetic algorithm. Now, why we would use this for an optimization of a mechanism problem is because it is a fairly complex solution space. And by creating all of these individuals initially, we're evaluating a large area of the solution space. And then we're saying, let me take the best ones and breed them to create better offspring. And then I'm going to still create some mutants. And those mutants then will explore the parameter space basically so that I won't get stuck in local minimas and hopefully reach the global minima. So in the next video lecture, we'll talk about how to use this on an actual mechanism design problem.